This is video lecture number 10. Now, in the last lecture, we talked about measures of central tendency, right? Mean, median, and mode. But the second kind of information that can be conveyed by descriptive statistics is variability on any given group of measurements. How spread out are they? How much do they differ from each other? Or to put it another way, what is their degree of dispersion? Sort of a fancy way of saying it. So we saw in the last lecture in the grade curve example that a lot can in fact depend on the variability of data if you're using a mean to describe your data set. Now, in the legal arena, I would say measures of variability are often more important than the other measures of central tendency. The really good example of this are studies on sentencing disparity. So in jurisdictions that give and have historically given judges a lot of leeway on sentencing, you will often see really great variability among judges in choosing a criminal sentence, even with the same conviction offense and very similar pre-sentencing reports on that particular defendant. In fact, the studies that were done on sentencing disparities in those jurisdictions that gave judges a lot of discretion are what in fact led to the national move toward more structured sentencing guidelines that give less discretion to judges. We're going to go back to that example in a couple of minutes. But on this slide, you see the data that is listed in the Monahan and Walker book on page 92. A simple example here of two data sets. So we've got data set 1, data set number 2. These are just two groups of 4 IQ scores. So each of these two groups, here's group number 1, 4 IQ scores of 102, 99, 103, and 96. And group number 2, also 4 IQ scores, and those are 128, 78, 93, and 101. So each of these groups, as you can see, has a mean of 100. If we add these 4 numbers up and divide by 4, if we add these 4 numbers up and divide by 4, in each case, we're going to get a mean of 100. But in group 1, we really see that these scores here have pretty low variability, right? Whereas these scores are much more broadly dispersed. So this is a classic example of how if you just describe a data set with a mean alone, that might not tell you enough about your data. And in fact, you're also going to almost certainly want to know the variability. So the 3 measures of variability talked about in the Monahan-Walker book are the range, the variance, and the standard deviation. Now the range here, of course, that's the simplest one. The range just consists of the difference between the highest and the lowest scores. Sometimes it's in fact just listed as the highest score and the lowest score. So here, to go back to our IQ score groups, the range of group 1 here is 103 minus 96, or a range of 7, whereas our range here of group 2 goes from 128 all the way down to 78, so a range of 50. Now calculating the range, very nice and simple, but if you think about it, you can see that it might be a problem to just use the range or even the mean plus the range to describe your data. And that's because the range really only takes into account the highest and lowest scores in your data set and doesn't really convey enough information about your data because it's essentially leaving out all the points in between. Whatever points are in between here, we don't know what those are, right? Same thing over here. We just can't tell where those in-between points would fall by just knowing the mean and the range. So ideally, we want some measure of variability that will take into account all of the scores, all of the data points, and not just the highest and lowest. And in fact, using statistical formulas to determine variance and standard deviation are what is going to do that. These statistics, variance and standard deviation, are going to give scientists more and better information about the actual dispersion of scores because they do take into account all the scores and not just the highest and lowest that we look at for range. So this makes intuitive sense, I think, and the book gives a great example of how misleading it might be to just have a mean and a range using that sentence disparity problem. So here we have a data set. We have taken 100 judges in our study. And what have we done? We've given all 100 judges the same offense conviction, the same case facts, and the same probation report. And we've asked our judges, what sentence would you impose in a case like this? Now here's our data. One judge said, I would impose a 1-year sentence. One judge said, I would impose a 20-year sentence. And 98 judges, so the vast majority of your judges, all said that they would impose sentences of 6 years. All right, so now if you wanted to describe your data here and you calculated the mean that you would come up with would actually be 6.1 years. If you use that to describe your data, you'd be pretty accurate because really here we had this large sample size of 100 that sort of protected our mean from these two outlier values. But if you tried to use the range to describe your data, of course, that would be very misleading. If all you said was, well, I surveyed 100 judges with these same facts and same reports, and they issued sentences from 1 to 20 years, even though that's a true statement, right? They did issue sentences from 1 to 20 years. It's not very accurate at all, and it's sort of misleading, right? Because in 98 out of 100 judges, you had, in fact, absolutely no variation. Okay, so to get a better idea of the dispersion of scores, you can calculate the variance, and then from the variance, you use that to calculate the standard deviation. Both the Monahan and Walker book and Statistics Without Tears, I think, have very good explanations of this. If you need to review those, I think both of those sources are excellent sources. Okay, let's talk first about the variance. So variance really is just a measure of the average deviation from the mean of all the scores in your data set, the average deviation from the mean. So how spread out are your values from that average mean number? Now, at first glance, you might think, if we were just going to calculate variance, how far away all our values are from the mean, why don't we just add up all of those variation measurements and divide by the number of data points and be really simple about it? But if we do that, I think mathematically you can do this calculation and show yourself that if you actually did that, the answer would always be 0. Because if you have your mean, by definition, it's perfectly balanced, so that the sum of the deviation on one side is equal to the sum of the deviation on the other. So let's look at our little data set that we have here, which is the same one in the Monahan and Walker book. In fact, let's imagine that this is a data set of 5 judges and the sentences that the judges imposed in a particular case. Okay, and the data set consists of 3, 4, 5, 6, and 7-year sentences issued by the 5 judges. Now, this is a nice simple data set. It's very easy to calculate here that the mean of the data set is 5. So we surveyed 5 judges. They all gave us the sentences they would impose. The mean there is 5. So if we were going to use just the straight deviation from the mean to try to calculate our variance, what would we get? We would get, okay, this value is -2 away from the mean. 3 is -2 away from the mean. 4 is -1 away from the mean. 6 is +1 away from the mean. 7 is +2 away from the mean. If we add all those together, -2 plus -1 plus 1 plus 2, we've added them all together, and what did we end up with? 0. That doesn't tell us anything about variance. So what scientists do to solve that problem is they first square all the deviations from the mean and then add them and take the average of that. That is the definition of variance, the average deviation from the mean. So now this line down here shows you doing the actual variance math here with our data set. So the number 3 is -2 away from that mean of 5. So we take -2 squared. The number 4 is -1 away from our mean of 5. So that translates into -1 squared. 5 is the mean itself, right? So that's 0 away from the mean. Data point, next one is 6. That's +1 away from the mean. So that's reflected here. And our last data point, of course, is +2 away from the mean, and that is depicted here. Now, if you actually do all that math, square all these numbers, you get 4 plus 1 plus 0, of course, plus 1 plus 4 equals 10. Now we have to take the average of that. The average, of course, is we divide by how many data points we have, which we have 5 data points. So we get 10 divided by 5, and we end up with a variance of 2. Okay, a variance of 2. So in our, if we imagine this is judges, 5 judges meeting out these sentences, they gave out sentences of 3, 4, 5, 6, and 7 years, right? We could calculate the variance there, and we would say the variance is 2, but the question is, to what? This is a problem, because our variance formula here that we came up with requires us to square all of those deviations. Now, you'll remember from your high school math that if you square numbers in a math problem, you also have to square this unit of measurement up here, right? Like, for example, a simple one, when you figure out the area of a rectangle, right? The area of a rectangle that's 3 feet by 4 feet, the area of that rectangle is just going to be 3 times 4, right? 12. But the area of that rectangle is then described as 12 square feet. 12 square feet is the area. So you have to square the unit of measurement at all. But now going back to our sentencing example, it just doesn't make sense here to talk about a variance in judges' sentences of 2 years squared or 2 squared years. So how do scientists solve this problem? Well, they solve the problem by taking the square root of the variance, the square root of the variance, because that then can be stated in terms of the original unit of measurement rather than the unit of measurement squared, okay? And the square root of the variance is called standard deviation. That's what standard deviation is. So again, looking at our sentencing example, if we calculated that variance, which we did on the other slide, as 2 square years, the square root of 2 is actually 1.4. If we take the square root of the variance, we also take the square root of the unit of measurement. So we're back down into a unit of measurement that makes sense. So the standard deviation in our data set here of judges' sentences, right? We've got a mean of 5 years with a standard deviation of 1.4 years. Okay, so the question is, well, aside from, math being really fun to do, why do we care about standard deviation? What's so cool about standard deviation? Well, one reason we care about it is that scientific data is often explained using the term standard deviation. So it's very important for us to have an understanding that the standard deviation is going to be some indication of the variability of the data. How far away from the mean do our data points fall? But the even cooler thing about standard deviation, and the important thing to come away from this class knowing, is that if we know the mean score, the mean score in a data set, in a sample data set, and we know the standard deviation, then we can tell where the scores are going to fall around the mean of that data set. So this is best illustrated by looking here at our very familiar normal curve. We all know what a normal curve looks like. This is also in the Monahan-Walker book on page 94. Okay, one thing to remember about the normal curve, which I think makes sense, is that the mean, the median, and the mode, in fact, are all exactly the same. Now, data sets in real life hardly ever, in fact, probably never fall into a perfect normal curve, especially one sample set, not going to fall into a normal curve. But in theory, if you had an infinite number in your sample and you were measuring something like IQ, that by definition does have a normal type distribution, you would more and more and more approximate the perfect normal curve. Normal curves are also referred to as bell curves, as illustrated here. I'm going to ask you to pause and read this cartoon. It's very funny. Go ahead and read it and then start the video again. All right, so here we've got a real life data set. In this case, it's a set of exam grades, just sort of plotted out here in order from the high of 98. We go down and then back up, down, back up, down, back up, down, back up, and down to our low of 57. Now, it's kind of hard to make a lot of sense of this data looking at it laid out this way, but if we take this data and do something different with it here, and if we lay them out on a frequency distribution graph, now you can see, although our curve is not by any means perfect here, right? We've got a little bit of up and down. It still does approximate that normal curve shape. So this actually, I think, it's a lot easier to get a quick view of where students' scores on this particular exam fell. Another classic example is flipping a coin. If you flip a coin 100 times, and I were to ask you how many heads do you think you'd get, you'd probably guess, well, I would guess that I would get 50. Now, this is, of course, assuming that our coin is perfectly weighted, so it's equally likely to come up with heads or tails. Okay, so that would probably be a pretty good guess if I asked you that question. But the truth is that on any one attempt at flipping that coin 100 times, any one sitting, you were going to sit down, flip it 100 times, you might end up on any one of those attempts with a more outlying statistically unpredictable result, like maybe one time you flipped it 100 times, you'd end up with 75 heads and only 25 tails. And if we take this further, if we had identical coins, evenly weighted coins, gave one to each person in our class, and each of you flipped your coins 100 times, well, now it's likely that a few of you would get more outlier type results. And if we had at least a class of 30 students or more, and we did this exercise and plotted all the values of the number of heads, we'd probably get something reasonably approximating a normal curve. Now, if we did this with 1,000 people or 10,000 people, and each of them flipped a coin 100 times, and we just kept plotting the number of heads, we'd probably get something more and more and more closely resembling our perfect normal shape curve, right? We'd certainly get lots of values here in the center between 45 and 55 heads, right? We'd get a few 25, 75 combinations, and even a few way out here, on the edges, the 95 heads, only 5 tails kind of combinations. Okay, now I want to go back to standard deviation. So here, what we have on this slide is the graphic illustration of the concept of standard deviation here on our normal curve. So if we know the mean, which is of course going to fall right in the middle, and if we calculate the standard deviation using the mathematical formula, or more likely these days, if you're a scientist, you're going to have a computer calculate the standard deviation for you. But if we do that, we actually know that about 68% of the values of our data set are going to fall within one standard deviation of the mean. So that means 34% of the values of our data set will fall above the mean, 34% will fall below the mean. We also know that about 95% of the values are going to fall within 2 standard deviations. Okay, within 2 standard deviations, either above or below, right? So that's going to be about 47.5% above the mean, 47.5% below the mean. We also know that about 99% of the values are going to fall within 2.5 standard deviations. So that's going to be, right about here. I don't have that one up here on the slide. But we know that 99.7 of the values are going to fall plus or minus 3 standard deviations from the mean. Now, some simpler explanations in various sources use 3 standard deviations to encompass 99% of the values, but as you saw in statistics without tiers, 99% is actually 2.5 standard deviations, and moving up to 3 standard deviations then gets you all the way to 99.7%. So for the purposes of this class, I want you to use those numbers because they're more precise. Now, let's use this curve and go back to say a judges and sentencing disparity example. Let's say we did our study on our 100 judges. We took 100 judges, gave them the same facts and reports, and we got a mean sentence here of 12 years. 12 years. But we also calculated the standard deviation of our judge data set, and we found that the standard deviation was 2 years. So knowing our mean of 12 and our standard deviation of 2, we now also know that 68% of the sentences are going to fall between 12 plus or minus 2, right? So between 10 and 14 years. We also know that 95% of our sentences will fall within plus or minus 2 standard deviations, right? So plus or minus 4 years. So 95% of our sentences fell here between 8 and 16 years. And in fact, we know 99.7% of our sentences fell between 6 and 18 years. So again, knowing both the mean and the standard deviation gives us a lot of great information about our data on our judges. Okay, here's another image of a normal curve. Here you see this little symbol here that looks a little bit like a cursive U, I think, or a really fancy cursive M. This symbol is actually mu. You're going to see this symbol used to depict the mean, in particular the mean of a population. The other symbol you see on this diagram is this one. Looks like a little letter O, a little tail coming out up here. That symbol is sigma, and sigma is used to depict standard deviation. So here you see mu in the center of our nice normal curve, which is the mean, and then you see mu plus or minus 1 standard deviation here. And that's, of course, translates into 68, well, here it's 68.2%. Of the values falling within 1 standard deviation of the mean. You see the same for mu plus or minus 2 standard deviations and plus or minus 3 standard deviations, and the percentages here that's going to encompass. So these portions of the values here, 68.2, 95.4, and 99.7, also translate into what we sometimes refer to as the 68, 95, and 99.7 confidence intervals created with 1, 2, and 3 standard deviations away from the mean. And I'm going to talk more about what confidence intervals are later. But I did want you to notice that both in this normal curve and this next one, I'll illustrate that often when you see a normal curve like this, it's actually going to be an accurate histogram where the area here under the curve at various points is going to represent an actual quantity. So this is a histogram showing dispersions of IQ scores on a particular IQ test. We know IQ tests are normed, so the mean is going to be 100. So the blocks of space here under the portion of the curve, for example, let's look at this one. This little area here is 14%. And because this is an accurate histogram, the area that's depicted here in this mustard yellow color is actually 7 times greater than the area depicted here in the aqua blue color. So if you gave this IQ test to 1 million people, say, at random, you'd actually expect 14% or 140,000 people out of 1 million to score 14% here between 20 and 85. You'd expect 14% to score between 115 and 130, okay? And you'd expect 2% or about 20,000 people to score between 55 and 70, and so on. Okay, so far we've been talking about normal curves, but remember, not all data sets that are graphed are going to form into a normal curve. Here are some examples of right and left-tailed skewed curves. So when you're naming a skewed curve like this, whatever side has the long tail on it, that's how you name the skew. Okay, so when there's a right skew here, you're going to see your tail coming out onto the right. The other interesting thing about a skewed curve like this is unlike the normal curve, right? A normal curve, remember, mode, median, and mean were all the same right there in the center. But what happens when you have a skew is that the skew pulls the mean further away, pulls the mean in the direction of the skew. And that sort of illustrates this idea that outliers in your data, right, can pull your mean toward them. So when there's a right skew, the outliers in the data are going to pull that mean toward the right. And of course, with a left skew, that's going to pull your mean further to the left. And on this last slide, I have this is the income distribution of the United States. Certainly, this is always going to illustrate a skewed curve, right? So definitely charts of income in the U.S., starting over here on the left with zero income, and moving on up here through $50,000, $100,000, $150,000, and so on. So certainly charts of income in the U.S. are going to be right skewed curves with those high income outliers pulling the mean up higher than the median, right? See, the median income is 46,000 or so, right? But the mean income is actually higher than the median because those outlier high earning households pull that mean toward the skew. So the mean income is actually going to be higher than the median, and maybe a sort of a less meaningful number here in a case like this. All right, that is the end of video lecture number 10.